Welcome to this session on operations research. In continuation with our discussions on simplex method, in this session we will discuss one more problem, which is a maximization type again, but which involves two decision variables and three constraints. In the previous session we have seen the steps in simplex method and how the final solution is obtained, the optimality or the optimal solution is reached, and how you conclude or how you ascertain that optimality is reached depending upon the Cj minus Zj values, and also interpret the solution and also find the Z value. If it's a maximization problem, find what is the Z maximum in terms of that is the best possible or the optimal solution for the given problem. We will take one more problem, another problem in this session, and try to get more insights into the simplex method. In this problem, the problem given is again maximization. Maximization Z is equal to 23A plus 32B. So the decision variables are A and B here. The constraints are 10A plus 6B is less than or equal to 2500, 5A plus 10B is less than or equal to 2000, and 1A plus 2B is less than or equal to 500. So there are three constraints, two decision variables here. In the previous problem, in the previous session, we saw LPP, again maximization, where you had three decision variables and two constraints. Here you have two decision variables and three constraints. And of course, in addition to these three constraints, that is 10A plus 6B less than or equal to 2500, 5A plus 10B less than or equal to 2000, and 1A plus 2B less than or equal to 500. The non-negativity constraints are also there, which is decision variables A and B both are greater than or equal to 0. Now, since the equations are of constraints are of less than or equal to type, that is LH is less than or equal to RHS, we introduce slack variables now. These slack variables will be 3 in number here because there are 3 constraints. So we add S1, S2 and S3 to the objective function, and we get the objective function as maximization Z is equal to 23A plus 32B plus 0S1 plus 0S2 plus 0S3. Maximization Z is equal to 23A plus 32B plus 0S1 plus 0S2 plus 0S3, because the coefficients of these three decision variables, the slack variables rather, these are the slack variables. A and B are the decision variables. S1, S2, S3 are the slack variables that you are using. These are the slack variables. S1, S2, S3 are the slack variables which will have a coefficient of 0 in the objective function. And the same slack variables will be introduced in these three constraints. In the first constraint, 10A plus 6B, you have to now convert this particular inequality sign into equality sign. So you are adding one slack variable here, that slack variable S1 you are adding, slack variable S1 you are adding to the first constraint. So 10A plus 6B plus 1S1, the coefficient of this slack variable S1 will be 1. As we have seen, all the coefficients in the constraints will have, all the slack variables in the constraints will have a coefficient of 1, whereas the slack variables will have a coefficient of 0 in the objective function. So the first constraint here becomes 10A plus 6B plus 1S1 plus 0S2 plus 0S3. So here only slack variable S1 is added in the first constraint. S2 and S3 are not there, but you can consider that S2 and S3 with the coefficients of 0 respectively are there in this particular constraint. So you can read it as 10a plus 6b plus 1s1 plus 0s2 plus 0s3 is equal to 2500. Similarly, second constraint 5a plus 10b plus 0s1 plus 1s2 plus 0s3. So in the second equation only s2 will be there with a coefficient of 1. So 5a plus 10b plus 0s1 plus 1s2 plus 0s3 is equal to 2000. Similarly, the third constraint where only s3 will be there with a coefficient of 1, s1 and s2 will be having a coefficient of 0. So 1a plus 2b plus 0s1 plus 0s2 plus 1s3 will be equal to 500. Again 1a plus 2b plus 0s1 plus 0s2 plus 1s3 will be equal to 500. And a, b, s1, s2, s3 all will be greater than or equal to 0. So this is the standard form of your simplex. In any simplex method, this is the standard form in which you have to now introduce slack variables with the coefficient of 0 in the objective function and slack variables with the coefficient of 1 in the constraints respectively. Let us see the simplex table now. So in the simplex table, as you can see here, this is now represented here. You can see here 1, 2, 3, 4, 5. You have 5 decision variables or 5 variables here. 5 variables. It has 2 decision variables and the 3 slack variables. So totally it adds up to 5 variables here, and you have 3 constraints. You have 3 constraints. So 1, 2, 3, 4, 5 variables and 3 constraints here. And also, if you now look at this now, you will now 5 minus 3, so 2. What you will do now, a and b will have now this a and b will be now not coming in the basis. You will be adding or you will be including s1, s2, s3, the slack variables with coefficient of 0. These are the unused resources. We have seen slack variables are the unused resources. So s1 is equal to 0, s2 is equal to 0 and s3 is equal to 0. These 3 initially will come into the solution. A and b will not come into the solution. Your objective is to now find out values of a and b. You want to find the values of decision variables which will optimize this particular LPP, this particular model. Okay, but initially in simplex method you are taking s1, s2, s3, these slack variables in the basis here. Now what will be the values that you are going to write here? What will be the values? As we have seen here, the decision variables are written here a, b. This is the decision variable a, decision variable, this is decision variable a, this is decision variable b, and these are the slack variables. Whatever is appearing in the objective function you have written here. Whatever is appearing in the objective function you have written here in the basis. These are the basis. But what is the coefficient that will be writing under this Cj? This Cj is the coefficient of these variables a, b, s1, s2 and s3 in the objective function. So a has a coefficient of 23 in the objective function, b has a coefficient of 32 in the objective function, s1 has a coefficient of 0, s2 has a coefficient of 0 and s3 also has a coefficient of 0. Similarly, when I go to the equations now, in the first equation, a has a coefficient of 10, b has a coefficient of 6, s1 has a coefficient of 1, s2 and s3 have coefficients of 0, and the solution is 2500. It is 2500. Similarly, in the second equation here, second constraint, a has a coefficient of 5, b has a coefficient of 10, s1 0, s2 1 and s3 0 again, and the solution here is, or the right hand side value here is 2000. So that will be written in the solution. This 2000 will be written in the solution here, 2000. Similarly here, third constraint, if I take this third constraint, 1a plus 2b plus 0s1 plus 0s2 plus 1s3 will be equal to 500. Will be equal to 500. Will be equal to 500. equal to 500. So this is how you enter. As we have already seen in our previous simplex problem, and we did it in our previous session. I'm again repeating this for the benefit of those who are now getting introduced to simplex method in this video. Refer the previous part also of this particular simplex method. So this is the table now. Now we have to now see what is the Zj value. We have seen Zj value will be initially when S1, S2, S3 all have a coefficient of 0, then your Zj value also becomes 0. So Zj value is 0 initially. 0, 0, 0 and 0 here. 0. That is 10 into 0 plus 5 into 0 plus 1 into 0. That is 0. Similarly 6 into 0 plus 10 into 0 plus 2 into 0. That is also 0. 1 into 0 plus 0 into 0 plus 0 into 0 is 0, and so on. So you get all values as 0. What is Cj minus Zj value now? This Cj value, that is 23 minus 0. So 23. This will be 20. Cj minus Zj. For this particular column, first column, Cj value is 23, Zj value is 0, so 23. So this will be 32. This is 32. This will be 0. This will be 0. And this will also be 0. So this will be the initial simplex table for you. Now in this particular table, you can see again it's a maximization problem. So your optimality is reached only when Cj minus Zj values is less than or equal to 0. Only then you can say this maximization problem, any maximization problem will be optimal. This is a condition for optimality. Cj minus Zj values should be less than or equal to 0 for a maximization problem for optimality. So, but here you can see Cj minus Zj values are all 0 or positive. That is, Cj minus Zj is greater than or equal to 0. So this solution is not optimal. So now what you have to do? You have to see which is the highest positive value here. Highest positive value corresponds to this particular column. This particular column. So this now becomes your key column. The column containing B. Decision variable B now becomes your key column, because that is the highest Cj minus Zj value, and all the elements in this key column, now will become the individual corresponding to their respective rows, the key row elements for the key column. For example, if I have to now find out the ratio now here, ratio in the first row, ratio will be solution, that is 2500 divided by this number here, this 6. 2500, this is a solution. 2000 ratio is equal to 2500 divided by this key column element in the row. In this first row, the key column element is 6 in the first row. So 2500 divided by 6, because solution is 2500, the key column element in this row is 6. The key column element in this first row is 6, so 2500 by 6. Similarly, for the second row, it is 2000. The solution is 2000 divided by, what is the key? 10. 2000 by 10. And for similarly for the third row, it is 500 divided by 2. 2500 divided by 6, 2000 divided by 10, and 500 divided by 2. So now if you look at this, you can see here which is the least ratio. We have seen, you have to select now the least ratio out of these three. What is the least ratio here? You have to find out now. You can see here, It's the same table. You can see here 32 was the highest number, so you selected this particular column. This particular column you selected. And similarly, when you found out the ratios, 200 was the minimum. So what you did is you selected row 2. So this will now become your key column. This is the key column. This is the key column. This is the key column, KC, or the key column here. And this will now become the key row. This will now become your key row, because the least ratio corresponds to this. So this will be your key row, KR, key row. And the intersection point here, this will become your key element or the pivot element. This particular element 10 here will become your key element or the pivot element. So now key column is this involving B. So now B will now become your entering variable. B will now become your entering variable, and S2, because it is corresponding to the key row, S2 will now become the slack variable. S2 will be the leaving variable. So in the next table, B will now become the basic variable. Now B will come into the basis and S2 will leave. B will come into the table and S2 will leave the solution. B will come into the solution and S2 will leave the solution. You can see here. Again, same thing here. This S2 will now be replaced. This S2 will be now replaced by B in the new table with the coefficient of 32. This 32. This is the value of B now, once B comes into the solution. So B will come into the solution now. B will come into the solution. Here is a summary of what we did. Now the column containing B is the key column and the row containing S2 is the key row. So the outgoing or the leaving variable is S2 and the incoming or the entering variable is B. The intersection element of the key row and the key column is called the key element. In this case, the key element is 10. Now converting this element into 1 by dividing each element in the key row by 10 and remaining elements in that key column as 0 using the formula. Same formula you use. New element is equal to old element minus the product of the key row element and the key column element divided by the key element. So now the key row was the second row because S2 was involved with it. So there it is not a problem at all. Divide all the elements in the old key row. In the old table, whatever elements were there in the second row, because that is a key row, you divide all elements by the pivot element or the key element, the intersection point 10, that is 10. So all elements in the new table in the second row where S2 has left and B has come in, all the values there will be the old value divided by 10. Old value divided by 10. So there is no problem with row 2. The problem is with row 1 and row 3. So in row 1, again the calculations are shown. This is the old value. Suppose I say row 1, the first cell in the row 1, 10 was the old value. So the new element will be 10 is the old element minus 5 is the key row element, 6 is the key column element divided by the pivot element. Pivot element is same. You can see here throughout the pivot element is 10. That will not change. What will change is the other values. So the row 1 calculations, practice this. So this is once you get hold of this, it's very easy. But you have to solve this. Just go watch this video, take a notebook and solve it parallelly. Understand this and parallelly try to solve simplex method on your own. Only then you will understand. So row 1 calculations here are shown. The new element is equal to old element minus the product of the key row element and key column element divided by the key element. So you have to now understand what is the old element, what is the key row element, key column element and also the key element or the pivot element. So row 1 calculation. So these values 7, 0, 1, minus 0.6, 0 and 1300 will be your new elements in the first row in the new table. Similarly, row 2 calculations, as I told you, this was the key row. So old element was 5 divided by the pivot element that you already got. Throughout all old elements, divided by the pivot element 10. That will give you the new value. So in the new table, in the second row, the values will be 0.5, 1, 0, 0.10, 0.10, 0 and 200. In row 3 calculations, again it will be, the new element will be old element, that is 1, minus product of the key row element and key column element divided by the key element. That will be 0. So in the new table again 0, 0, 0, minus 0.2, 1 and 100. So this will be the values in your new table now based on the calculations. Once again it is repeated, once more I am repeating, new element is equal to old element minus product of the key row element and the key column element divided by the pivot element. Whatever you get as a result of this for each cell or each particular place in row 3, that will be the new values of row 3. Similarly for row 1 and row 3 calculations you have to make according to this mathematical formula or this particular expression. So this will be your new table here. This will be a new table. This will be a new table. So in the new table again you will find out, so with all these elements are actually put in this table, you again find out the Zj values. The Zj values are again found out this way. You can, one thing is noticeable here, we can see S2 has left the solution, S2 has left the solution and B has entered here because B was qualified based on the highest Cj minus Zj value, and S2 left because minimum ratio in the previous step. So again you have to repeat the step here, find out Zj and Cj minus Zj values. Okay, B will have a coefficient of 32 because B always in the objective function has a coefficient of 32. So now what you will do based on this, you can see S1 and S3 still remain, S2 has left. Find out the Zj values. So 7 into 0 is 0, 0.5 into 32 will be 16, plus 0 into 0 is 16, that's why Zj is 16. Similarly 0 into 0 plus 32 into 1 plus 0 into 0 is 32. Similarly 0 into 1 plus 32 into 0 plus 0 into 0 is 0. Minus 0.6 into 0 is 0, 32 into 0.10 is 3.2, plus this one is 0, 3.2. 0 into 0, 0, 0, all zeros here. So Zj values you have got 16, 32, 0, 3.2 and 0. Now again find Cj minus Zj values. What is Cj minus Zj? Cj is 23, Zj is 16. 23 minus 16 is 7. Similarly here 32 minus 0, 32 minus 32 is 0. 0 minus 0 is 0. 0 minus 3.2 is minus 3.2 and 0 minus 0 again is 0. So that way you got Cj minus Zj values for the new table. So in this table now Cj minus Zj values, since all Cj minus Zj values are greater than or equal to 0, all Cj minus Zj values, now what you have to look now here is, be very clear now, you can say that there is a minus sign here, minus 3.2 here. But now you can see here S2 has already left the solution. It was here in the basis and it has now left the solution. It has now left the solution. So that you have to now look at that non-basic, whatever variables you have now in this particular solution, this one, this minus 3.2, this S2 was once inside the solution, it has now gone out of the solution. You can see here very clearly. So this need not be taken again. We will be considering only the other values now. When you look at these particular values now, all Cj minus Zj values are not less than or equal to 0. All should be less than or equal. You cannot see there is a minus value here, fine. But what is your objective now? All values should be less than or equal to 0. Since all Cj minus Zj values are not less than or equal to 0, the solution is not optimal. The solution is not optimal. Okay, so here you can see a 7 here. Now even if this was negative, you could have concluded that the solution is optimal. This clearly shows that there is a positive value here for a maximization problem, and there is a positive value of Cj minus Zj. It shows that an improvement is possible. An improvement is possible. That is, if I bring in A into this solution now, because there is a positive Cj minus Zj value, if I bring in A into the basis by taking out any one of these slack variables, then I will get a improvement. So what you have to do now is take this as, now there is no need of, there is no tie here, directly this 7 now, that's why it's indicated in say green here, which means this particular column now becomes the key column now, this becomes the key column, this is the key column now, this now becomes your key column, because there is a positive value, only one value is there, so directly this becomes your key column. And now take the, you know, the solution is 1300 by 7, this 1300 divided by 7, so 1300 by 7, if I do 1300 divided by 7, I think we will get 185.7, 185.7. Similarly, 200 divided by 0.5, so that will be 200 into 2, that is 400. 200 divided by half, that is 400. And this you will not do, because 100 divided by 0, you cannot get a value. 100 divided by 0, there is no value. So this is neglected now. Because 100 divided by 0, no, infinite. No, you cannot get a solution. 100, anything divided by 0. Okay. So you have only two values now, 185.7 and 400. So clearly this particular row now becomes your key row now, because 185.7 is the least ratio out of 2. Minimum ratio is this. So now this becomes your key row now. So what it indicates? It indicates A will now become your entering variable. A will become your entering variable, and S2, S1 will become your leaving variable now in the next table, next iteration. And this 7 here will become the intersection element of the key column and the key row. So this now becomes your pivot element. This now becomes your pivot element. So similarly, now we have to draw one more table here with the new elements. Same consideration, same way as you have done before. So the column containing A, is the key column, and the row containing S1 is the key row. Outgoing or the leaving variable is S1, incoming entering variable is A. Intersection element of the key row and key column is called the key element. In this case, the key element is 7. Convert this element into 1 by dividing each element in the key row by the pivot element, that is 7, and the remaining elements in that key column as 0 using the formula. Again, new element is equal to old element minus product of the key row element and the key column element divided by the key element. So here the first row was the key row here. So the calculations in the new table will be simple. The new element will be individual elements in row 1 divided by the pivot element, that is 7. So in the new table, every element in the row 1 will be divided by the pivot element. 7 divided by 7 is 1, 0 divided by 7, 0, and so on. So in the new table there is no problem in row 1 calculations. In row 2 calculations, same, new element will be old element minus key row element into key column element divided by the pivot element. So all these calculations are again based on the same formula which we have so far discussed. You have to calculate it on your own. So only if you exercise on your own or you calculate on your own, you will understand. The sample calculations are shown here. You can just attempt it and just find out how you get the elements of the new table. This will be a new table now. This will be a new table, the second iteration. So in this iteration, second iteration table, you can get here A has now entered the solution, S1 has left, B has already entered in the first iteration, so S2 had left, S3 remains here. Now A will have a coefficient of 23. Its profit coefficient it's a maximization problem, so we call it as profit coefficient. If it's a minimization problem, we call it as cost coefficient. So here it's a maximization problem. So the profit coefficient of A is 23 and the profit coefficient of B is 32. So that comes into the basis now. This now become your basic variables. Basis comes into the basis, and all these values which are calculated according to the calculations in the previous slide will come here. You can see the solution also is written here. the ZJ values are calculated. You can see here 23 into 1 plus 32 into 0, that is 23. Similarly, 23 into 0 plus 32 into 1 plus 0, 32. 0.143 into 23 plus minus 0.07 into 32 plus 0 comes to approximately 1. You can check, approximately it comes to 1. Similarly, all these values calculate. What you have to do is all x values into this cost of the coefficients of the basic. These are CB here refers to the coefficients of the basic variables, CB. So the individual values of the coefficient of the basic variables into the values that you have written here into this particular cell, which represent the coefficients of the variables in the constraints. When you multiply that and add all the summation of all that, that ends up to this, that will be your ZJ value. For example, if I take this 185.7 into 23 plus 107.14 into 32, that will roughly come to approximately, maybe decimal place here and there. I have rounded it off, so maybe there may be slight changes depending upon what decimal values you take. Rounded it off, approximately it comes to 7,700 here. And you can see here Cj minus Zj values 23 minus 23, 32 minus 32, 0 minus 1, there is a negative, minus 1, 0 minus 2.6, minus 2.6, 0 minus 0 is 0. You can see here all Cj minus Zj values are less than or equal to 0. This is a maximization problem, so the solution is optimal. So since all Cj minus Zj values are less than or equal to 0, the solution is optimal. What is the value of a solution? A basic variable, that is A has a value of 185.7, B has a value of 107.14 when the optimality condition is reached. A has a value of 185.7, B has a value of 107.14. S3 is unused resources, slack variable, that you are not considering. Its coefficient is 0. That will not come into picture here. So the final solution for this particular maximization problem is A has a value of 185.7, again rounded off to some decimals. We can either retain it in the form of fractions or decimals. We are doing it for academic purpose, so you can either take fractions or decimals. I have retained here decimals. You are free to take these values as fractions also, depending upon whichever is more easier for you. So A here is 185.7, B is 107.14, and when you substitute it in the objective function, Z maximum is equal to 23A plus 32B, we get a solution of rupees 7,700, the maximum or the optimum value for this particular maximization problem. So this is the second problem that you have solved in simplex method. Similarly, we will be solving, we have to practice more problems and then understand how this simplex problem works. So basically with this, one thing that you have to understand here, this A's values are not this. Again, I am repeating, these are the coefficients of this A and B, the coefficients in the objective function, the profit coefficients. These are not the solutions. The decision variables will have a value of 185.7, A 185.7 and B will have a value of 107.14. When you substitute it in the objective function, you will get a value of 7,700 rupees. So this is the solution for this particular problem. Thank you.